Ready to start? Good afternoon, ladies and gentlemen. My name is Larkin Liu. I'm a data scientist at Loblaw Digital. This presentation is about a research paper that we worked on earlier this year with my collaborators Richard Down and Joshua Reed, who's not here because he's studying at Waterloo. The paper was published in a conference, Canadian Operations Research Conference 2019, where it was part of the proceedings of that conference. So let's, quick survey of the audience. By show of hands, who considers themselves more of a applied data scientist? Sort of more focused on applied things. Who considers themselves more of like a research-based data scientist, doing more research-oriented stuff? So I guess, today's presentation is going to lie, very much in the middle of those two spectrums, the applied and the sort of research side. We try to present something that we're actually going to implementable, something proven to be implementable, something that's proven to be useful, immediately useful, that is, and also dive a little bit more into sort of the theory behind both established approaches and new approaches. So let's talk about the business problem at Loblaw's, because I think all data science problems should start with the business problem, because what are we trying to build here? We're trying to build things that are going to increase the revenue, increase the profitability of your business, right? Fundamentally speaking, is what we're trying to do. So this office you see here operates something known colloquially as click and collect, where you click something, you collect something, but more in depth, what it means is it's an online ordering system for groceries. So you can go on the website loblaws.ca or is loblaws.com. I think loblaws.com. I think both will go there, I think. And then you can go on there and browse an assortment of items available to you simply by searching. And search is the product that my colleague Angshuman over there works on daily. But after you search for your product, you're going to get an assortment of items which you can order. And so down that pipeline, you want to make sure that when you do order these items, people can actually pick them up when they go to the store and pick them up. So the inventory is true. It does match what realistically is there. And so the focus of this presentation is not to talk about that whole process. It is complicated in itself. The purpose of this talk is to discuss, in the circumstance where you have a variety of different algorithms running side by side, to pick and choose which is the best algorithm to use in order to show the right items on a website, such that you go to the store, you pick them up. It maximizes something we refer to as the fill rate, which means the percentage of items which you ordered online, which you've actually were able to pick up. And realistically and hypothetically, there are multiple algorithms running simultaneously to try to optimize that fill rate. And so this brings us to the whole idea of A/B testing, where you have to test which one of these algorithms is going to maximize on fill rate, or whatever metric you want to optimize on, to get the most profitable results from your technology. So when I say profitability, let's try to abstract this into a more abstract idea. It's referred to as reward. So reward can be anything that you do something, and then is anyone in the room familiar with reinforcement learning? So the reward is what you get when you sort of do something, and then some utility comes back from the environment. So In the multi-armed bandit scenario, it's kind of also like reinforcement learning, though it's a little bit different, where you have a reward, and when you do something, you get a reward in return. And we define not so much the reward, but the regret. Whoa. Sorry, the wrong thing. Apologies. The regret. Oh, it's not working on the screen here. I can't see it. Anyways, they regret RT in equation 2 as the difference between what the current reward we get and what the optimal reward would be if we would have played the best game possible. So pi star represents the optimal policy, the best hypothetical game that we can play, and pi is the current policy, how we play the game in the current time. And that's basically about it. And so in this work, we're trying to minimize regret. We're trying to minimize the regret of testing multiple algorithms side by side. And so let's think about some very basic strategies to, if we're testing multiple algorithms and they have multiple stochastic behavior returning, how can we maximize or minimize the regret that we get? So that we try to almost always play what's known in multi-armed bandit, the best arm possible, the optimal arm. And so a very simple way to do it, where the worst case scenario or the dummy scenarios where you kind of run everything with equal partitions, but if there is one optimal policy, then your regret is n minus 1 arms or k minus 1 arms times the regret of each of those plays. So you want to play the best arm for 90% or a majority of the time. And so this is what epsilon greedy does. It says we estimate the reward of the functions, the stochastic functions, as just a window estimate from before. We can use a variety of estimation techniques, but after we estimated usually it's averaging, but it could be other techniques as well. And after you estimated these estimate rewards, you just played a one that you believe is the best based on your estimate, and you play them with 1 minus epsilon probability. And then you play the other arms with epsilon minus 1 probability, epsilon over k minus 1 probability. And so, for example, if your epsilon was 10%, you'd be playing 90%, what you think is the best arm, and then based on your previous estimate, and then you'd be playing, epsilon over k minus 1% of the other arm. So if you had 3 arms, for example, it'd be 90% to your best arm and then 5% to your other arms. That way you don't waste that much money, on your experimental costs, and you minimize regret. So anyone see a immediate problem with this approach? It's pretty good. It's pretty good. You're maximizing you're exploiting the best arm, but is there a fundamental issue with this approach? If anyone, yeah.
Since the parameters and odd time changes, if you're only
that's beyond that issue. A more basic issue, a more fundamental result from this approach. That is what we address in the paper. Yes.
Okay.
Yes.
This will never converge on an optimal solution. Because you'll always be exploring.
Yeah, I think I know what you mean. The term I'm looking for is, it's always going to have constant regret, as you can see in this scenario, because you're always, even though you're playing majority, the best arm, you're always epsilon is that. So you want to, as our gentleman said over here, you want to converge on an optimal solution, where you're playing like almost always the best arm, not epsilon, not asymptotically bounded by epsilon. And so someone, came up with UCB-1, I believe, 2002, came up with this algorithm called UCB-1. And basically, he's going to play, the arms with the probability, you got to compute this metric called MT, which is proportional to the time horizon, how long in time horizon has it been, and inversely proportional to the number of arms that you play the arm K. And so when you try to play the arm that maximizes MT, what you eventually get is you'll eventually converge you eventually converge into the optimal, always playing the optimal arm. This convergence is a little bit slow, we found out experimentally, but it does, address the constant regret issue from the previous case. So, yeah.
Can I ask a quick clarification question?
Yeah.
Could you just walk us, because with all the terms, I lost keeping track of. Could you just walk me through the algorithm, maybe algorithm 1?
Which one?
Just the pseudocode, yeah.
Right, so
just reminding me of what the terms are.
Okay, so just go real quick. We have enough time, by the way, right? So Q represents the reward history, the observation history, and then from 0 to capital T to the end of your time horizon, you want to compute your omega. Your mu from omega. So omega is the reward functions in general, and then mu, if kt is what your estimate of the reward is for that specific arm at time horizon t. And then k is the one you're trying to maximize for. So once you compute for each of them, you compute the maximum, and then you play k with probability 1e. So you can do like uniform function and random sample it, and then you can play the arm that it's sampled out from. And then you add that observation into your Q record history set, your set of rewards, and then you can keep using that to compute your future parameters. And this one is almost the same, but we're maximizing on this metric called MT, which is calculated down here. So it would be your estimated reward, just like how you calculate an epsilon greedy, with this correction term that's proportional to the time horizon, but inversely proportional, or is also going to be reduced by this number of arms that you play the thing. So that's basically it. And experimentally, this hypothetically does converge to an optimal arm, but we found that the convergence, and you can read about it, the convergence is a bit slower than you would like. So, a little bit comically, in 1933, someone, this was in 2002, right? In 1933, someone came up with, or a brilliant gentleman named William Thompson, came up with something known as, Thompson sampling. Yes.
Can I have a question? So M is just other term for.
It's a unique metric.
Unique metric form arm of under this UCB-1 algorithm, or
it's a unique metric in the UCB-1 strategy that would determine whether you're going to play the arm or not.
Mm-hmm.
Yeah.
Okay. Thanks.
And so, a bright gentleman named Thompson introduced a Bayesian method for this. So, similar to the epsilon greedy approach, where not similar, but like in acknowledgement of the epsilon greedy approach, where there is this constant regret because you're always playing with epsilon probability. Thompson developed, an approach where you sample from the probability distribution that you hypothesize to be. In our case, our probability distribution will follow Bernoulli distribution, because whether you sample, whether you can either fill the item or not fill the item, it's 0 or 1, and it has a probability of getting filled or not filled based on how the algorithm does. So that's how we chose to model this scenario, and it makes sense. And Thompson introduced a way where you would basically, sample from your hypothetical distribution and play the arm that maximizes from your sample draw, and then using that observation, you add it to your Q history, this Q array history, and then use that to keep estimating the parameters of the sample. So it's a sample estimation approach. So you would get your probabilities, and then you would put your parameters into Bernoulli distribution, and then sample those from those distributions. The one that returns the highest value is the one that you play. And so this compared to UCB1 actually has a higher convergence rate to the optimal arm. We found that experimentally. Why that is, it's just, Bayesian people would tell you it's better. But I cannot explain exactly why that is the case, and that's why I fall back at my applied guide. I can't really explain why it converges faster. But it also allows, at some very minute times, the play of another arm. So hypothetically, this should also take care of the non-stationary case as well, because it would hypothetically play a second arm, it with 99.999% play the optimal arm, but it's always, because it's a random sample, keep in mind at line 6, it might always pick something else outside of that distribution, that for a 3 sigma chance, that is a tail end that you get, and you might play the other arm. So that's the beauty of it. And in my work experience, in my life of reading papers, this method is found to be one of the more promising approaches to the multi-armed bandit strategy. Okay, so I guess, do we have to have an intermission here? Because Serena told me to put it in, a slide in for intermission. I can give an intermission, but
So are you going to the results of discussion next?
Not exactly. There's one. Yeah.
Maybe just do it right before the.
Okay.
After each of these ideas,
Yeah.
there's a break between results and
Yeah.
other.
Yeah, because the results go pretty fast. So anyways, so all right. So false alarm, no intermission, but so now you've sat here for roughly some time and say, so what was the original contribution of our work? What was the original contribution? And now we're going to get to that, right? So we've explored multiple ways in which we can tackle the multi-armed bandit problem, and what is the original contribution of the work. So let's look at the definition of non-stationary functions, right? A stochastic function, by definition of being stationary, means that it's always going to have a constant expected value, whereas a non-stationary one, this expected value changes over time. And just to add, we're gonna use this in the homo-escadistic terms. I forget how you pronounce that word. It means constant variance. So we're not exploring the hetero-escadistic. I forget how do you pronounce that. I always forget it. But constant variance assumption, just to make things a little bit more simpler to analyze. And so in a stationary case, this expected reward is a function of the parameters, and in a non-stationary case, it's a function of time and the parameters. So that's basically what it is. This thing's a little bit fast. Okay, so we came up with something called we are way ahead of that. The delayed feedback scenario. So as I mentioned earlier, this is a little bit tricky because we try to measure the fill rate, and we can only get our results back when the customer retrieves the item, after the point of sale occurs. So there could be a 1 to 3 day delay in which you've shown the item on the site, and then 1 to 3 days later, half a day later, you're getting your measurements back. So that's a problem that we face uniquely, and some other organizations do face as well. But some other places, like let's say you're building an app in a game on a mobile phone, you might get the reward immediately because it happens right away. But in this case, that doesn't happen right away. So that's something we need to take into account. And the non-stationarity case. So why non-stationary? Because we hypothesize, and it is somewhat true, that there's just more customers and things work differently in the weekend than they work on the weekdays, for example. And this is just one form of seasonality. People like to eat different foods on different seasons. So looking at, and we'll see later in the work that we're trying to use a seasonal, deterministic function to model the non-stationarity. A seasonal model makes some sense. And so we have the two scenarios. We have non-stationarity, and we have delayed feedback. And so, given that, we decided to come up with what we call the adaptive greedy strategy. So what we do is, in long story short, instead of we changed the way in how we estimate the parameters, such that it's gonna forget about things that are too far from too far back in history. It's gonna focus in the moment, but it's not gonna re-estimate everything like If we forget about everything, then we have to re-estimate from the beginning. That becomes a little bit troublesome, as you'll see, because you have zero idea what's going on a refresh, and you have to get that instant regret to replay all the arms equally again. So we propose an algorithm that is going to not refresh itself completely, like epsilon greedy would do, and also forget things that are too long in the past. And so we, yeah, so that's basically what I just talked about. And with, this is a, geez. Yes, so the time frame which we use to estimate the parameters is a moving window. That's a fixed length, and we forget about longer periods in time. And we play the number of optimal arms just like how you do in the epsilon greedy approach, where you play n star t, and then for non-optimal arms, you use the epsilon greedy approach as well. So that's basically it. The window which we use to estimate these parameters they don't use all the data, they use partial of the data, and also they are immediately from the past. Their most relevant data is used, not any data. So it's the window right before, or some time window before the next observation. And so we put all these metrics and ideas into a simulation. And we simulated both the stationary case and the non-stationary case. And so we have results to present. Should I stop it now for a break? Okay, yeah.
Could you offer some clarification on what I just want to understand? So
Yeah.
n is the number of instances, like number
It's the number of times you play that arm. Yeah. Yeah. And then everything else is the same as the epsilon greedy stuff. So it's not that much different from epsilon greedy, actually. Okay. Yes.
Capital N, that's the total times you've done an arm or within your window?
This is the total number of arms that are available.
Oh, total arm.
Yeah. Yes.
Could you explain a bit more about the delay in the system? Like,
Yeah,
where
so-
does this come from?
That's a good question. The paper is titled yada 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 with delayed feedback. The delay in the system is something that we had to incorporate in the simulation because it was the way in which our e-commerce platform functioned. If we'd worked in another industry like ad tech or something like that, or banking, or I don't know, something that doesn't have delayed feedback, we probably wouldn't have the term delayed feedback in this scenario. So it is a weakness in our paper. I think is a weakness in the paper that we don't really address delayed feedback very well. We kind of just incorporate it in the simulation, and then we address mainly non-stationarity. And so that's my answer to that question. So yeah.
Do you predict the delay, how long the delay is when somebody orders something versus how long it takes for them?
I think in this simulation we just kept it constant. It was a 1 day delay.
Okay.
Yes.
So I still have some question about the delay feedback.
Yeah.
So when you see the delay feedback, for example, we take actions from time t equals 1 to time t to t. Then for the delay feedback, do you mean that at time t we do not know the first from 1 to, for example, to r for the early history? We don't have the early history, or we don't have the recent history.
So if you imagine it, there would be, if we try to use this adaptive greedy approach or this epsilon greedy approach, you would not have the reward histories, t minus some delta in that most recent time frame. That data is gone, so you don't have that. So everything is from t minus delta and back. So that's how we incorporate it into the simulation itself. Yeah, in exact terms.
Anything else?
So assume you have your function, reward function is a period of t, and your time delta is greater than t. How do you think things would
no
react?
reward history for that delta period. So all the parameter estimates would be unavailable to you. You wouldn't have any knowledge until you at least pass delta t, or delta.
So it
Yeah.
just did not work.
Yes, there'll be some sort of cold start going on. Yeah. Yeah. Whereas if there was no delayed feedback, there would be an immediate sort of, after the first play, the second play, you can already start to do something. With the delayed feedback, you have to, the algorithm starts with the delta into it and it'll start. And yeah, that's the answer to the question.
All
Anything
right,
else?
let's take 5 minutes then.
Very quickly, we'll go over the results of our simulation. So in the stationary case, we just compared the sort of established algorithms, but with delayed feedback. And we found that, Thompson sampling performs the best, and you have this very variable and non-ideal performance for the UCB-1. And it's actually epsilon greedy is preferred. And this is a counterintuitive, but hypothesized is because UCB-1 just doesn't have a strong enough convergence fast enough to the optimal arm, and that's why it's always having a lot of regret. And that's what I hypothesized it to be. And based on the results of simulation, we would ideally use Thompson sampling if it was a stationary process. Now, more interestingly, now in the non-stationary case, well, in the non-stationary case, where, as I mentioned earlier, and now we're simulating, for example, here, we simulate visually, we simulate two arms whose true reward functions one is kind of like a lighter shade of yellow and the other one's a darker shade of orange. Yeah, it's not a very good choice of colors, but, and so they kind of, in one time period, one algorithm's better than the other, but in the second time period, the other one is going to be better than the other one's going to be better than the other one than the first one. And so when we compare our adaptive greedy strategy with an epsilon greedy strategy, we see that that turquoise curve representing the aggregate greedy strategy follows the optimal arms a lot better than without modifications, just a straightforward epsilon greedy strategy. And similarly, we can also this results in the regret being less over time in general. And we can extend this two-arm sort of example into multiple arms. We set k is equal to 10 in this case. We have 10 competing arms, all with a different optimal time period. And a cumulative regret comparing against both epsilon greedy and Thompson sampling. Thompson sampling does a bit better than epsilon greedy, but adaptive greedy has a much lower cumulative regret and higher reward because it adapts to that time period and it doesn't sort of have to relearn the parameters as you go along. And so that's basically the main results of this paper. A couple works that we might want to read into. A couple gentlemen asked me here, how does that log bound in UCB-1 is a non-constant regret? Read that paper. You can learn about that. Why? Our paper 2002. Chappelle and Oliver talk about Thompson sampling in more depth, and sort of this bringing back Thompson sampling into the 21st century after a 70-year layoff. This paper talks a lot about that. Our paper, which is basically going into detail about what I just talked about, and the original, Thompson sampling, I just put that in there. It's from 1933. I mean, it's gonna be hard to find, anyways. But yeah, so these are a couple of useful resources you guys might want to read up on if you have time. And that's about it. Just not related to this project in general. I do work at Lala Digital, but right now I'm on paternity leave because I have a newborn. But I am working, and that's my priority, of course, but I am working on a paper on reinforcement learning, actually. It's in the preliminary stages, so if anyone's I'm looking for collaborators. If anyone wants to collaborate, you can shoot me an email. That'd be great. That's about it. I guess that's really all I have to say. Yeah. Cool.
Nice. Let's open up for questions.
Yes.
What's your email?
Can you guys forward it on the screen or somewhere? It's LIU period.
Do you want it available to everybody online?
Yeah. You just put it on. I was gonna put it on a slide, but yeah.
You can put it on a slide channel or just put it on the YouTube.
I'll give a personal and my Loblaws email, but I don't check the Loblaws email that much anymore. I'm on leave, so I'll check the personal a bit more. But yes, I'll leave them both. Yeah.
So I have a
Quick question from the last page of your of the figure. Could you clarify what is mu A and mu B?
This one?
I mean the one before the one with this one.
So mu A is we put this in there to create a 2. And this idea was actually taken from another paper that we read that demonstrated the same thing. But mu A represents the function that generates the expected value for the stochastic function. So the expected value at any point in time follows this sinusoidal behavior. That's what mu A, and it's a function, as I mentioned earlier, it's a function of time and the parameters, not just the parameters. So that's basically what mu stands for. And in statistics, mu represents average. Though it's not always average, but we just chose mu, just for simplicity's case. Yeah.
Why did you choose a sinusoid as your?
So as I mentioned earlier, the grocery game is a very seasonal game. Weekends are fundamentally different from weekdays, and you get winter is different from summer, and so under this assumption, using a sort of seasonal periodic stochastic function is appropriate. I think that's the reasoning behind it. Yeah.
Do you think the result changes if the variance is much smaller than that?
So I also mentioned earlier, we're restricting the study to the homo-escadistic, or however that's pronounced. It's the constant variance assumption.
Constant variance. Sorry, I mean just the difference between the maximum and minimum of like that sinusoid.
I guess with more like market research, you can sort of pinpoint exactly how that. A more in-depth study probably like what's the real demand forecast during that season, and then sort of actually put in the simulation exactly the spread in the case, and probably that'd be a better approach. But there was no it was 100 days in the simulation here, as you can see. So it's a daily thing. There is no, as you can see here, there's a small delayed feedback here. Nothing picked up until it started rolling, and yeah, so it's a 100-day simulation, as you can see in this particular one. No general like deep thought was thought about which weekend or which seasons played in the are appropriate. But in the future, it's probably going to be more useful. We say, how about we have a switch in the weekends, or how about every Wednesday is a switch, or how about every season you have 4 seasons, they all have different optimal algorithms for each season, or different marketing campaigns. We kind of inject them, and then it changes the behavior of the algorithm. This would probably be a more in-depth, more relevant study of what how a grocery chain actually operates. But in a high level, this was purely to generate a seasonal, non-stationary stochastic behavior. Next question. Yeah.
Can you comment more on the application side? I think in the first slide you talked about what you work on at level of digital, and then you talked about the paper. Can you make a good connection with the two?
Yeah, so the content of this paper is primarily simulation work. Before you deploy any technology, it's always good to simulate things, and because it has a very low cost associated with it. If you actually deploy things, so the funny part is, you're going to deploy these black box algorithms that we kind of keep proprietary. And then even to create the mechanism that kind of throttles between different experiments should be simulated before to make it sure, okay, this is the one we want to use in our scenario. Because again, you can blindly use epsilon greedy, you can blindly use Thompson sampling. But if you run a simulation and we have a sort of a gauge, hey, this in our scenario, epsilon greedy works very well, or in our scenario, UCB-1 is the best one to use. So then it's all your software engineering efforts developing that, or developing something that's unique to you that will work for you. So that's basically what it is. Before the software engineering starts, you want to have a good idea of what's going to happen if you invest X hours into building some technology.
So what is the technology that you're implementing?
Multi-Armed Bandit for picking and choosing between different fulfillment algorithms, so to speak.
Okay, the fulfillment algorithm.
Yes.
For this epsilon greedy with refresh, Could you explain what's happening in the algorithm when it refreshes here?
Yeah, so it basically just wipes the slate clean, and then
So
has
it
to
forgets
re-estimate.
all the previous
Yes.
observations?
Yeah.
Okay.
And that's the standard way to do it. Or you can not do that and just keep all the history, but you'll always remember that from the past, and it really messes up the estimation in a non-stationary case. So your regret gets really high. So in our case, we kept the window very short, but with the delayed feedback.
So I'm not sure if I'm missing something or reading the graph wrong, but what does it mean when your regret goes negative? It's in the other plot too.
Is there a negative? Yes, there is negative. Cumulative, or is it cumulative or instant regret? Well, yes, it can hypothetically happen because we're measuring expected regret, not the, the reward is a stochastic function, so it's not expected regret. So stochastically, sometimes it can actually go above what the expected reward is, right? So then when you subtract it, sometimes it will go negative, and that's what happened. If it's only expected regret that we're minusing, or expected reward, then it shouldn't go negative, but it's not. It's the stochastic behavior. So imagine these sinusoidal curves with some noise on top of them. Yeah.
Yeah, so I'm quite happy that we see more and more papers regarding reinforcement learning right now. I see that the hype from 80s or when that was is getting back. And my question actually would be, would you see any other algorithm related to reinforcement learning which would be compatible to this one? And again, we can stay in that environment of inventory of grocery store.
So yeah, as the gentleman mentioned, it's a kind of reinforcement learning. Though reinforcement learning in the traditional sense is a little bit more complicated. Well, it's an understatement. It's actually a lot more complicated, but this paper explores, it surveys the state-of-the-art methods. It surveys state-of-the-art methods, and it builds on the pre-existing methods to try to modify it, and then it simulates in our specific use case to see what the performance is. So to answer your question, it already surveys, the first part of the paper just surveys state-of-the-art stuff. The second part, we change some previous algorithms and we simulate it in our scenario to see how it performs. To answer your question.
I have a question about the simulation. Are you taking kind of like the distribution of current customers and current customer behavior, or because I imagine for fulfillment there's long tail customers and there's long tail items as well, right? Like how do you get good, meaningful feedback from those?
No. In this simulation, as I mentioned Aaron earlier, it'd be useful to actually look at business data, like what the actual customer behavior is on a day-to-day or a week-to-week or a month-to-month basis, and sort of create these function generations from the actual behavior over the course of 2-3 years maybe. This one is just purely, we assume a seasonal non-stochastic case and we see how well it does in that case. So the short answer is no, we didn't look at any specific customer behavior data. We kind of thought experiment this sort of behavior and put it on. And I completely agree with you and others who are going to say, would it be more useful to actually base this off of more realistic data? And the answer is yes. The answer is maybe we have actual weekend, weekday differentials. We have seasonal differentials, and we start to interpolate scenario, and then we measure the cumulative regret accordingly. So yes, and that will require a lot more iterations. It will require just running more simulations. But I hope this is sort of like the first step in the deep end for that, to say, hey, this type of thing does improve the minimize the regret, and we should do more analysis to see in your company's specific use case, can this be useful? Because every company is going to be different with their own needs and requirements. Yes.
I don't know if you went over this, but how do you decide when to do a refresh of the algorithm?
Well, it's an arbitrary time period. In this case, I think it was like once every 5-7 days, a week or so.
Okay,
yeah.
So you just do it every periodically, basically. You
Yeah,
don't
it was
have
it was a constantly periodic time arbitrarily determined.
Okay. Do you think you could do like something that like detects when a refresh is necessary?
No, because the Multi-Armed Bandit is supposed to do that. That's what it's supposed to do automatically. It's not supposed to have another algorithm to determine when it's going to refresh. It has to do it by itself. The algorithm itself is supposed to be able to fully encompassing play the best arms at vast majority of the times, without you having to tune an extra parameter to tell it to do so. So, yeah.
But in your adaptive greedy, there was some time window, which I assume you put in by hand as a parameter.
Yes, that would be a parameter you put in by hand, and that would be something that that you kind of fix in place, but you're not expected to touch that moving forward. Okay. It's not supposed to be something you sit down and tune every day and sort of adjust.
For this particular simulation, you would have tuned it.
Actually, I don't recall. This is a very how do you say?
There's a clear period to the reward function here.
Yeah.
So you would have tuned the adaptive greedy parameter to that.
So you're saying, could tuning be the result of the improvements and not actually the improvement in the algorithm? And that actually is another weakness. Yeah, we haven't proven the fact that us giving that. So my response is, the time window period is not something you're expected to iterate or change over time. It's something that is supposed to be you set at one time and leave it. Same with that gentleman when he talked about the refresh period. And also, believe it or not, we didn't actually tune anything. We kind of just arbitrarily set these numbers. But this paper hasn't conclusively proven whether manually tuning of this is the cause of the improvements and not the algorithm itself. And that is a weakness. That is a weakness we should definitely conclusively say. We've also iterated various time windows, and it also didn't show. Also showed the same results over a variety of time windows. And so that was a bit, I guess, an oversight, and we should improve on that. Yeah.
Did you also try different epsilon value and see was 0.1 the optimal one that you choose?
Short answer, that's from the very beginning of the paper. Epsilon greedy strategy is very well established in literature already, so the short answer was no. We just kind of picked, I think, 10%, and we just rolled with it. We kind of know what's going to happen with it, and so yeah, we could iterate through a variety of combinations, but I think that parameter would be the least one you want to iterate over because it's already well established. Yeah. Any other questions?
All right, if there aren't any more questions, let's just thank the speaker.